Okay, well, thanks again for joining me today. Today we're going to cover MEG Energy Christina Lake asset as part of our lecture 4, I think, session. So again, the idea is that for your project, we define the project objectives, project deliverables, descriptions, critical success factors, project assumptions and constraints, and the research data required. So we're gonna do a little bit research, looking at some papers. We're gonna extract data through AccuMap to understand the data a little bit better, what SAGD versus NCG looks like, and then we're gonna construct a small simulation to compare SAGD versus NCG co-injection. For the project deliverables that I shared with you, there will be a report detailing usage of NCG during SAGD operations and better understand its benefits. Of course, the question is always, do we need this technology? Why would we use it? What's the benefits, advantages, and the disadvantages? And by extracting this data from public domain, we're going to be able to compare the data sets and better understand the dynamics. And then through a small simulation, we're going to be confirming what we actually see in the academic literature, what we see in the field data, and confirm that with reservoir simulations. And the teams already picked their assets, so which is good. So we have two big broader teams, but we basically aggregated those to 5 assets. So we have one entity picked Sermont, another one picked Sunrise, so Synovus's asset. We have MEG Energy, so that's going to be the discussion today. We have Lismer Athabasca, and we have Jackfish at Canadian Natural. Okay, so today we're going to talk about MEG, as you can see in the slides here. In the above slide, I'll zoom in a little bit more so you can see a little bit better. So we have basically a little bit of a lifespan production plot. So typically what happens is that in green, you will have oil production rates. So you can see those assets have barely any decay in oil production rates. So it's fairly continuous. And it's really a function of steam injection rate, which correlates with the oil production rate. And steam injection rate, as you can see here, is always in red. So this is like the convention in our industry. Steam is red and oil is green. Now, if we take the ratio between the two, what is the name of that ratio? Can we see in the comments? What will be an important ratio between the steam injection rate and oil production rate? Okay, awesome, good job. So many of you answered SOR, steam to oil ratio. And we can see this is really dividing the red line by the green line. Now, on the right side, we can see 2 indicators there that talk about other SORs, CSOR and ISOR. What do you guys think is I stands for and C stands for? So I and C. What does that stand for right here? I and C. Let's see. No, not condensate. No. So what this is, initial. No. Good tries though. So I stands for instantaneous, and C stands for cumulative. And really, what it means is that what is the SOR right now as we speak, kind of on dailies, on hourlies, on weeklies, instantaneous, right? Like what's happening as we speak. And C is aggregation of all the I's, so the cumulative SOR. So just like we have cumulative oil production, we will have cumulative SOR, which is aggregation of all SORs. And so what you see here, the dotted line is ISOR, right here. So this is the one. So right now that SOR is just above 2, and cumulative SOR, CSOR, is the kind of this black line, which is much cleaner, so it's not as noisy. But you can see it's very close to the ISOR value, so almost the same value, but it's not as noisy. So this is almost like a broader kind of indicator of the the overall trend for the asset versus instantaneous behaviors, right? So if this thing going higher here, there could be an instantaneous reason for it. What do you think happened in this region that makes you believe that maybe one shouldn't worry much about the instantaneous SOR for this specific time frame? What do you think happened there? Because if steam to air ratio going higher instantaneously, it may be a bad thing. But if on cumulative it doesn't really change much, maybe we shouldn't be as worried. But what do you think happened here that makes us believe that maybe we shouldn't worry that much about that SOR? Because remember, high SOR is bad, low SOR is good. So here we shouldn't worry about that, but why? Maybe they increased the area they were producing. Okay, that's a good answer. Yeah. I will be more kind of specific technically on that, but maybe we can have some other views here on what's going on there. Look at this chart here. And look at this chart here. Okay, let's see. Okay, we don't see any other answers for now. But what really happened is that they increased significantly, as you can see here, their steam capabilities going from 15,000 barrels injection rate to close to 35,000 barrels of, cubes. So that's, to convert to barrels, you need to multiply by 6.29. A significant capability here of increasing CPF, central process facilities capabilities, generating steam, treating emulsion, and that resulted in proportional increase. Yeah, okay, good job, John. But that resulted also in huge uplift in oil rate, as you can see here. So oil rate went from 5,000 cubes a day, which is 30,000 barrels a day, to about 13,000 cubes per day, which is like what, over 70,000, right? And here right now we're at 100,000 barrels a day. So basically what I'm trying to say is that this increase in instantaneous SOR wasn't that big of a deal, but on cumulative kind of smoothened things out for us, make things a little bit more logical, understanding from a broader trend perspective. That's why it's important to keep this in mind. Now, what's also happening here, you can see, is that every once in a while, they have scheduled CPF turnarounds. As you can see here, it says, right? So this results in basically shut-ins or intermediate shut-ins on some of the CPFs, right? Or, I mean, okay, I didn't say it right. Not some of the CPFs, but kind of like some of the facilities within the central process facility. For example, here you can see that steam rate significantly declines here, 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 and here. And that results in oil production decay, which is here, here, here. But they have to do it because they basically want to maintain their facilities. So they have to inspect them, fix things, keep things clean, make sure there's good integrity of those facilities, make sure there's no corrosion. So they have to do this once in a while. So usually you can see the time frames when they would do it, right? So this will be on average like every couple of years, maybe once a year, something like that. Depends on what they're trying to do. But that results in fluctuations in the ISOR, instantaneous SOR. But you see the SOR chart in black is very smooth. So the broader range tells us this is a good, clean asset with very kind of little volatility when it comes to the steam to oil ratio, if you discount basically all of those other activities like turnaround. So basically maintenance timeframes. Okay, what is the other thing we're observing here? So what we see here is water to steam ratio in purple. So what will be like the importance of water to steam ratio? Why is that parameter important? So WSR, water to steam ratio, it's right. It's close to 1. It's about 1.1. But why do you think it's useful to know that parameter? Water to steam ratio, WSR. So the importance of that parameter is that you inject steam and that steam is condensing. And then you produce it in the form of water. And so basically you monitor what is that water in relation to oil production, right? So that's kind of the importance of that. The other thing we can see here in this chart is the in yellow gas injection rate. So you can see exponential gas injection rate going basically from 0 in 2014 towards about 2,000 E3M3 per day. So 2 million cubes per day. How is this related to your project, you guys think? How is that yellow line related to the goal of our project? It's NCG co-injection, right? So the yellow chart is NCG co-injection, so gas injection. And then we can also see the producing well count. So right here in the gray line. So this will be right now close to 300 wells, producing wells. I think it's about 294 to be honest. And the other thing we see is steam rate. We covered that. We covered bitumen rate, which is in green. We covered water rate, which is here. So that water to steam ratio is that one in blue over red. We covered ISOR. We covered producing wells, gas injection rates, water to steam ratio, and the CSOR relatively to ISOR. Okay, so the other thing we don't see here is the gas production rate, but otherwise we see everything. Unless you guys can see the gas production rate. I don't see the gas production rate. So I can see only those things. So steam, bitumen, water, ISOR, CSOR, WSR, gas injection rate, producing well count. So if we think about the units for those things, so on the y-axis, the primary y-axis, you will see, okay, so I'll address that question in a second. So when we see steam, bitumen, water rate production, it's all in volume, so cubes per day. Again, you can easily translate this to barrels per day, so BBLs per day, right? This is basically density close to water, so it's not oil equivalent, it's pure barrels, like because of the density. And well count is just well count. The unit is the count of the wells. Gas injection rate, as I said, is standard E3M3 per day. So basically we would call this something in the industry, we'll call it decks. So you get 2,000 decks, right, a day. But this is 2 million cubes per day of gas injection rate to maintain that entire operation on that asset, which right now produces about 104,000 barrels a day. And then we're looking at unitless ratios, which are ISOR, CSOR, WSR. Okay, let's address your question. Wet steam has lower usable heat energy than dry steam. Yeah, so that's a good comment because it's really a function of steam quality. So if you have lower steam quality, so if you have lower heat transfer to the pay of the reservoir, and therefore you have by definition lower enthalpy. The unit for enthalpy is joules per kilos, and that the energy per mass injected is lower heat energy transfer to dilute the oil to be produced by gravity, which is what SAGD is about. I know it sounds like a very complex sentence that maybe I overcomplicated, but is that kind of clear what I tried communicating? Is that okay? Yes. Okay. Awesome. Okay, let's see for some other things. So we covered basically the production plot. So when you guys go and extract data from the public domain, in our case, we're using AccuMap, you should have something similar that you plot that looks like this. Okay, so we want to plot oil production rates. We want to plot steam injection rates. We want to plot ISOR. We're going to plot CSOR. We want to plot WSR. We want to understand the injection of the yellow line, which is NCG co-injection with the steam. By the way, what's interesting here is that you can see kind of plateau of steam injection rate as the NCG injection rate increasing. And then we see this behavior in oil production rates. Then you get another leg of steam injection rates, oil production uplift because of the heat transfer. but that also correlates with gas injection rates in yellow, which is also intriguing. So there's lots of kind of intermediate or instantaneous learnings about all of those kind of behaviors. And on the cumulative basis, you can see that the SOR in overall is not increasing. The SOR, the cumulative SOR, actually declining over time, and this is something you would want. So MEG Energy, Christina Lake asset is doing a really good job in cutting CSOR slowly over time, while actually boosting oil production, which is positive for their economics. Okay, so let's kind of go over in this document. And by the way, we're discussing public domain D54 document from Christina Lake from June 2024. So let's talk a little bit about the resource. So this is original bitumen in place, OBIP, and this is cumulative bitumen production here. This is the area, this is the OBIP, and this is cumulative oil production, right? So you can see in their project area, they have about 4 billion barrels, right? So 4 billion. The development area where they produce is about 2.2 billion. And combined active well pattern, where they're currently extracting bitumen that's in place, it's about 0.8 billion. So 0.8 billion, 891 million. Cumulatively, they produced about 359 million barrels, okay? So if we go back to the chart that we just looked at, so this one, so over the course of those daily production rates in green line, so let me switch it to green right here. So over the course of this time, since January 2008, MEG Energy Christina Lake produced 359 million barrels a day. I think that was the number. So then they basically aggregate that, right? Aggregate the daily oil production and end up in that third, 0.3 billion barrels of oil produced, basically. So right here. So this will be 0.3 billion barrels of cumulative oil production. But look at this. So the cumulative recovery factor on the asset is only 9%. Only 9%. From the development area is 16%. And from combined active well pattern is 40% as of this date. So they have another, 10 years to go at least from the current kind of combined active well pattern area as they continue introducing more pads and kind of increasing that value over time. But then they can kind of go into, further development area that they have. Soon we will see the map where they're at. So basically what this tells you is that the company is not running out of their reserves anytime soon, which is a big positive, right, for them. Okay, so let's see what other things I want to talk about. So the typical reservoir parameters within the development area. So we're looking at average pay height is 24 meters. So what do I mean by that? Is that when you have injector and producer, and they develop the steam chamber, so they inject here and produce here, that pay area is 24 meters. 24 meters. So this will be that. The porosity range within the steam chamber or within that pay area is about 30 to 36%. So 0.3 or 0.3 porosity. And saturation, water saturation is between 0.18 to 0.4. So you will have an SW value, SOW, and SG value. So those are the various saturations in the pay. So, but then you have very little gas saturation. So basically, if you add all those, you get equals to 1. But if you know that this is, let's say, 20%, so this has to be 80%. So you could have 80% SO, oil saturation. Now, you have horizontal permeability and vertical permeability in Darcy's. It's 5 and 2.5. So this is really the ability of the fluid to flow through porous media. And Darcy is kind of the measurement unit for that, as you learned in other courses. Then you will have something that's called initial reservoir pressure. So that's 2100. So then the injection is to that pressure. And then when you do that, you end up with something that's called bottom hole pressure. So bottom hole pressure, you inject to that initial reservoir pressure. So the bottom hole pressure could be higher than this pressure. And reservoir temperature is 13C. But here's a question for you guys. If you utilize steam that's been injected, and considering it needs to basically reduce the viscosity of that oil in all of those reservoir, what will be the injection rate for that steam if you look at the horizontal well? So what will the horizontal injector see when it comes to the temperature injection? What do you guys think the temperature could be? Based on your research. Higher. Yeah, it is much higher. Maybe we can get more specific. Let's flow some numbers. Let's guess some numbers based on your educated kind of. Let's see who is here even listening and see some numbers. It's okay to be wrong. I won't judge you guys. No, you guys are scared. Okay, so this temperature could be as high as 240 C. Oh, yeah, Alex, good job. 200, yeah. 200 to 40 to 30 to 20. And it's really a function of the vapor pressure curve and the bottom hole pressure injection, right? So bottom hole pressure, temperature, the volume in the chamber, and to maintain the chamber pressure and the reduced viscosity of the bitumen. This is one of the issues with this technology, right? It's energy intensive, and that's why NCG co-injection reduces the energy intensity, because by definition you don't inject as much steam. You co-inject with the methane, so natural gas, right? And that is being maintained in gaseous phase in situ. So this way, it doesn't condense like steam right away or water, right? Or not right away, but at the same rate on the vapor pressure curve. And it's able to maintain the steam chamber pressure. But obviously, one of the issues is that you may not have such effectiveness when it comes to heat transfer in situ. And in situ, I mean in place, like on underground. And so that's why we're doing this project, to better understand the benefits and the disadvantages and advantages of the NCG co-injection with SAGD. Is it clear? Is it good? So your task this week is going to be to extract. Yeah, thank you. The task next week is going to be to extract data from AccuMap to better understand performances. What we're going to do, we're going to extract data on the asset to understand the data. And then we're going to extract data on maybe at least one pad that saw an NCG co-injection and see what happened before and after, right? And this is just one example of you can see here well pattern reservoir parameters, bitumen in place, and recovery factor estimates. So here, let's pick one random pad. We will call this pad J right here, and do maybe like more of a zoom in analysis of the J pad. So this is a J pad. Maybe we can even find on the map, see where it's located. So you guys can have a better kind of understanding of where J pad is located. So let's see here. Can we see a J pad here? I see AJ here. Okay, here it is, right there. You guys see it? Right here. J pad. Pattern J. They call it pattern J. So this is the guy we're talking about right now. Okay, you guys can see it? So now, sorry, I keep asking you questions, but I obviously don't see who is even online and listening to me. So, but it's okay. So let's see what's happening on the JPad. So the area in square meters is 781,000 or 677. The net pay thickness is 21. So obviously you can see the chamber growth is going to be slightly less than a V pattern or pad, which will have close to 26 meters pay thickness. The average porosity on that pad, on that V, it's going to be 31.6. Here is 32.7. So we're dealing in slightly higher porosity. Oil saturation is 74. So remember how we talked about this? So oil saturation here is 74, so 74%, which means that water saturation on that pad is about 26%, right? So on that specific pad. Permeability 3 to 6 Darcy. Original bitumen in place is about 4 million cubes. SAGDable bitumen in place, so what can be SAGDed? So basically using our technology is about 3.6. So 80 to 90%, basically. Why is that? Why do you guys think that is? Why SAGDable bitumen in place is less than original bitumen in place? Okay, let's talk about that a little bit. Why is this number less than this number? Okay, maybe I want to hear from some other guys. I can see you online, but I don't know if you're actually listening. So why is SAGDable bitumen in place is less than original bitumen in place? Okay, so the reason is because of the geology quality. So you will have something that's called heterogeneity. Permeability, maybe, but we can't produce everything. Pore space, yeah, that's true. And the pore space actually not connected, perhaps, yeah. And that will be not connected because you could have, let's say, something that's called, and I'll type it, IHS, inclined heterolithic stratification, like this. I know it's a crazy wording, but so those really geologies that are kind of not permeable, they're a little bit more muddy, they have high mud content, and they can't really produce oil. But guess what else they're doing? What happens if those geologies are in the middle of our steam chamber? So remember our steam chamber that we drew here? Like what happens if that geology sits right here and right here or right here? It hinders the chamber development, right? And so that's why they're basically saying, look, we're taking into account the fact that maybe what we're able to produce through those reservoirs are not exactly what's originally in place. Maybe there are some kind of geological formations that, first of all, not as oil saturated, not as permeable, not as porous, but also maybe hinder chamber development. And so they will make some assumptions what those could be. So on this pad, the recovery up to date is 24%. Obviously, as we look at other data, like 65%, 50%, 47%, we can conclude this pad is maybe younger than the other pads. The estimated ultimate recovery factor is about 50% on the pad. And recovery to date from the SAGDable bitumen in place is about 26%. So we get 24%, 26%. And the estimated ultimate recovery SAGDable is 50 to 60%. So they leave a little bit of a kind of uncertainty, right? Because it's difficult to predict steam chamber shape, growth, coalescence, development, all of those things. Okay, so now I want to get a little bit more tactical about NCG co-injection. And let's talk about what the text here says. Oh, okay, so figure 8 shows all the wells by injection type. Co-injection of non-condensable gas, NCG, and steam is critical part of MEG's enhanced modified steam and gas push eMSAGP technology. The technology combines to use NCG co-injection and reduce well spacing, infills or SAGD well pairs to reduce the energy of SOR required to extract the remaining bitumen, freeing up steam for deployment of new wells. You see, they're talking about this, freeing up steam. So the goal is to co-inject NCG, reduce energy intensity, pressurize the reservoirs, but at the same time, you free up the steam and you reallocate or redeploy to new wells. This process is implemented after sufficient energy has been stored in reservoirs by the SAGD process and remaining recoverable bitumen is warm and mobilized, right? So they're basically saying, okay, I have the steam chamber right here, and I inject sufficient amount of steam in the reservoir here that all of that oil could be mobilized, and now I just pressurize with NCG. I take the steam that I used to inject and reallocate to a new pad. The steam and gas mixture contains the heat to remaining bitumen in place, resulting in reduced SOR. As bitumen rates decline, steam injection is reduced to further improve the SOR, and NCG injection rates are increased to maintain chamber pressure. It's exactly what I was talking about. MEG uses natural gas in its NCG injection process. Figure 9 shows instantaneous SOR, ISOR, NCG injection concentration, and cumulative SOR, CSOR, performance for MEG's phase 1, 2, 3, 2B well patterns. The use of NCG co-injection in concert with the use of infill wells in eMSAGP process has shown positive results. So remember, when they talk about NCG co-injection and infill wells, they're basically talking about this. I have injector here. Okay, let's use a different color. I have injector here and producer here. I have injector here and producer here. And I develop a chamber like this. And now I develop a chamber here like this. During the kind of later stages of chamber development, I'll put here something different. It's called infill well. So then I co-inject NCG in injectors, and I produce from that infill well as well. So there's another producer. So we get 1, 2 original producers, but now we have a third producer that is the infill well. Do we have any questions associated with that? Is it somewhat clear? Okay, awesome. The use of NCG co-injection in concert with using infill wells has shown positive results. Reservoir pressure targets have been successfully maintained. Remember, we talked about bottom hole pressure, so they specifically tell us what it is, which is amazing. Look, I didn't look at this presentation before I started presenting, but you can see, like in the industry, we all kind of use the same language, and you can tell that this capstone is industry oriented, as you can see, because everything I talk about, the company, without asking me or me asking them, saying the same type of words. So you can see how it's like translates to real world, what you're studying here. Lower steam requirements reduce the per barrel operating cost, as well as greenhouse gas intensity and water withdrawal intensity. Additional, the ability to free up steam capacity from operating wells for redeployment to new well decreases the capital requirement to increase production. NCG co-injection results in increased production gas rates, which is what we've seen. 75 to 80% of the injected gas is produced back from the reservoir and recovered. Consequently, additional gas sweetening units or recompression packages are required to treat the additional gas for reinjection. So here we have a very much reusable process where we inject something, we produce it, and then we reuse it. So this, from an environmental point of view, this is very beneficial. Steam generation equipment, no negative impacts to well integrity due to co-injection have been observed. So I think it's a good point. We kind of stop it right here. And we're currently at 34 minutes. And see if you guys have any questions. To my friends that working on MEG Christina Lake project, are you happy with what you were able to see so far? Is this beneficial? Is this kind of explaining a little bit The really huge benefit is that it's going to be posted and you can rewatch it as well. Okay, awesome. So this is a little bit more tactical, I guess, for the course. I did make videos like this in the past as well, but my memory sucks these days, so I don't even remember what I posted in the past. But this should be helpful. Any questions associated with NCG co-injection, MEG Energy, Christina Lake, all the parameters that we talked about, permeabilities, porosities, original bitumen in place, cumulative oil production, initial pressure, initial temperature. So the viscosity chart looks kind of like this, right, guys? So this will be temperature, and this will be viscosity in centipoise. And we basically kind of, here we're going to be at 100 degrees. Here we're going to be at 200 degrees. And here we're going to be at million centipoise. And here we're going to be at 10 centipoise. And this kind of looks like this. So you have to introduce the heat to recover, to transfer that heat to bitumen and then drain it by gravity. Okay, thank you, my friends. Thank you. Okay, so final chance for questions. I saw that some wells will develop the chamber by injecting steam on both ends in the beginning. At what point would we switch to just injecting from the top? And at what point can we switch to NCG? Yeah, so that's a good question. So for many years, over many, well, not many years, I would say the past 20 years, so 2 decades, various technology developers like myself tried implementing new unique techniques to reduce emissions, to improve SOR, to boost oil uplifts and reduce steam requirement. So some people tried doing different well configuration. Right now, for this course, we would just use basic SAGD configuration. And the injection of NCG at MEG in this specific case happens when you basically displace like the steam. You, as they said before, you kind of allocate that steam to new pads and you co-inject from the same NCG. When it comes to the injection time, this is another very interesting angle. Many people tried innovating in this space about timing of NCG injection. Lots of academic research about that. This is really a function of the geology, just like you see in this picture. And maybe let's draw another chamber and kind of talk about this. So you could have injector producer like this and chamber development. And you guys, we talked about IHS. So imagine this is one steam chamber. So you basically inject steam over time. And let's say after 5 years, SOR is 2, and oil rate in this well is 500 barrels a day. Now let's take another chamber that looks like this. And before it was developed, we have IHS zones that look like this. So those are like muddy barriers, inclined petrolithic stratifications. And so now this chamber, when it develops, it developed nicely originally. So originally it looked like this. But now when we actually want to try to draw what happens after 5 years, it may look like this. With the heat transfer like this. Something like that. So then after 5 years, this chamber will have SOR of 4, steam to a ratio of 4, because now you're trying to inject that steam to the bottom hole pressure, but the response of oil production is not as much because those non-permeable regions hinder chamber development, where ideally you would want it to be here. You would want that, but it's just not happening because of those complex geologies. And oil production rate could be, let's say, 300 barrels a day, like here. And why am I saying that? Because to your question, it depends. Maybe for the first chamber, you want to do it in later stages of the recovery, maybe after 7 years. But maybe with this second chamber, you want to do it maybe after 3, 4, 5 years, because now you need more steam and you don't get as much oil back. Does it make sense? Awesome. Thank you. Okay, my friends. Well, hopefully it was useful and you enjoyed that session. So for this week, submit your proposals. I adjusted the language. I think you should all be very happy with the language. I think it's very clear what we're going to be doing in this course. This week, as always, is what we talked before. Let me know if you have any questions, any concerns. No stress, please. Don't panic over anything. But this week, go to your individual assets and do 2-3 pages summary about kind of the stuff we talked about in this session. Like what is the production, what is the SOR, what is the injection rate, what is the production rate, where is the NCG taking place. So do that, and we're gonna aggregate that in your final report for all of your efforts. And next week we're gonna be working on extracting the data and analyzing those parameters that you guys are going to be talking about this week in your reports on SAGD NCG comparison performance, right? This is going to be basically what was done here, right here. So this is what we're kind of going to try to plot in the upcoming week. So next week and the following week for our individual assets. And obviously, the people that working on MEG Energy side, you kind of have a base template. You know exactly what it's going to look like, right? So if you get something that looks different, then and then you can also do the JPEG if it's in public domain, right? And if it's on AccuMap, you can extract the JPEG information and see if NCG was co-injected there, and see, like in the data in the table that we talked about, the JPEG recoveries, see if you get similar data. So that will help with your kind of analysis of SAGD versus NCG. Like, is that clear? I mean, the scope is very defined. So here I'll write it for you. The scope is defined. SAGD versus NCG. That's it. Like, that's what we're doing. And we're following 3 methods: academic research, data extraction, and small mechanistic simulation to confirm our analysis. For the specific well we choose, does it have to have NCG co-injection? Good question. So this asset, the whole asset, has NCG co-injection. Some pads may or may not have NCG co-injection. So when you extract data for the asset, it should have NCG co-injection. So my understanding, all of those assets do have NCG co-injection that we picked, that you guys picked. So that's good. But when you extract the pad data through your research about the asset, you should kind of see which pad will see NCG co-injection. And so then you just target that pad, right? So for example, for some of you that saw this presentation today, asking the question, does JPAD have NCG co-injection? I don't know. It may or may not, but that requires a little bit of an effort from your behalf to say, okay, I found the language in their public report or in the data that says that they inject NCG here, like non-condensable gas, they inject. So we see basically the yellow line, right? And therefore, I'm going to extract that data. So that's kind of the idea. Does it make sense? Because what we want to do, we want to understand the whole asset and one of the pads. Not all of the pads, but one of them as a sample kind of exercise. Remember, guys, this is like a big, our industry. This industry is over between Alberta and Saskatchewan, we produce over 2.2 million barrels using this thermal techniques, right? In situ thermal techniques, 2.2 million barrels. Alberta produces about 5% of world's oil production. 5% of world's oil production. So we can't work on everything, but we're gonna work on like things that are somewhat representative. So, and then when you go to the industry, you can say, "Hey, I know everything about this asset. I know everything about this technology, and I actually even studied this one pad that was optimized for via NCG co-injection." And then you can say, well, actually, maybe I don't like this technology that much because of those things. But you can also say, but I actually like it because it, cuts steam requirement and accelerated oil production and things like that. And then when you talk to your interviewers, you sound very educated on the topic from an experience point of view, right? So because you actually know what you're talking about, because you did the research, you extracted the data, you simulated some of the data, and it's just like the whole package, right? It's great. Okay, my friends, all the best. So we'll connect next week around the same time. Thank you. Okay. Bye bye.